let's talk about harmonic motion. Suppose I had an equation that looks like this, which would describe some simple harmonic motion. Equation. Now let's say I wanted to offer possible solutions to this equation for x. Well, I would need something that, when I take the second derivative, will give you back itself with this negative omega squared in front of it. That is, if I just move this term over, okay, so I just need to get out negative omega squared x from this equation. So let's talk about some possible solutions. Sine and cosine would both be good solutions, because if you think d by dt of cosine omega t, well, what does the derivative of cosine give you? It gives you back negative sine omega t, and then derivative of what's inside, omega. So the second derivative of cosine omega t would give you negative omega squared cosine omega t. And you can see that the same thing would work for sine, because once you get to a derivative of cosine, I'm going to get back a negative sine. So if I do derivative of, second derivative with respect to time of sine omega t, well, let's talk about it. The first derivative, so I'm just going to do one at a time, would be cosine omega t times omega. And then the next derivative would give me negative omega squared sine omega t. So those would both be true. Also, if I do simple addition of sine and cosine, that would be true, because you take the derivative of terms separately. So another possible solution would be cosine omega t plus sine omega t. And of course, these can differ by some constant. So I could have an a in front. I could also do the same thing up here, put an a in front of these, and it will all work out. So they can differ by some multiplicative constant a. Let's talk about one that wouldn't work. Well, if I do x of t equals exponential omega t, and again, I need to throw in that multiplicative constant. Well, what happens when I take the derivative of an exponent? Well, I get the thing back. So the first derivative of this, let's do it one at a time, d by dt a e omega t. My first derivative, d by dt, will give me back a omega e to the omega t, and you can already see the problem. We're not going to get a negative out, so this solution would not work. And similarly, if I were to do linear combinations of exponentials, so if I just did simple exponentials, I guess I should say, e to the omega t minus a e to the negative omega t, we might say, well, won't the sign on this one be changing back and forth? Sure, but then we have the problem of this one. Well, what can we do about that? The obvious thing, if I want to make the sign of the exponential change every time I take a second derivative of it, would be to throw in an imaginary part, right? Because then if I start taking derivatives of this, so second derivative with respect to time, a e I omega t would give me, on my first derivative, a I omega e I omega t, and then my second derivative would give me negative a omega squared e I omega t. And then I could also do the same thing I did with the sines and cosines and do linear combinations. So a final one that would work would be a e I omega t plus a e negative I omega t. The point is we just need that sign to change. And if you remember the rules about sine, cosine, and exponentials, you'll notice that we actually already showed that this one would work when we were working with the combinations of sines and cosines. I want to take that as a challenge to think about there. But these are solutions and non-solutions to the simple harmonic motion that this equation describes.